If you build an autonomous AI agent today, you will likely use a large language model to route tasks and pick tools. It feels incredibly flexible at first, but when you deploy it to production, this architecture scales terribly. When you hand an LLM a static list of 30 different tools and ask it to solve a complex coding problem, it has to guess. If a tool fails, the model tries again and again. This creates infinite error loops and massive latency before you get a single line of usable output. Worse, every time the model thinks about which tool to use, it has to read the entire tool schema back into its context window. Over a long session, this creates token bloat. You are paying the model to reread the rules of the system for every single step. Compare that to a standard Python script running a basic regular expression. The Python script executes in a fraction of a millisecond and costs $0. The LLM takes seconds and burns thousands of tokens just to decide if it needs to search a database. Relying entirely on an LLM for basic task orchestration is a mathematical and temporal disaster. You are effectively using a rocket ship to go to the grocery store. This is why we built the Antigravity architecture. Instead of an LLM struggling to juggle tools, we use a stateless, highly structured orchestrator designed to bypass these latency constraints entirely. This diagram shows the 4 distinct tiers of the system. System 1 handles execution. System 2 is the audit layer. System 3 manages memory. And System 4 acts as the strategy layer. Notice that the strategy layer, System 4, completely removes the LLM from the routing equation. All tool selection and workflow pathing happen in strict, deterministic Python code. Meanwhile, the actual intelligence tasks are split. The execution layer runs on fast cloud models, while the audit layer is handled by a secure, locally hosted model. A user prompt flows from the top down, passing through strategy and memory, translating directly into a specific, optimized tool recommendation before the LLM ever generates a token. Shifting the burden of intelligence out of the LLM's context window and into these deterministic code layers resolves the latency and cost paradox. To understand how this works at zero latency, we have to look at System 4B. This is the prefrontal cortex of the orchestrator, and it operates as a neuro-symbolic hybrid. The symbolic part is the skeleton. At the top level, it uses regular expressions with word boundary detection to parse human inputs. It doesn't need semantic understanding to know what you want. It relies on hard-coded, human-readable structure. But a static script isn't an AI. That's why we added the connectionist layer. Inspired by reinforcement learning models like AlphaGo, every keyword in the system has a distinct mathematical weight. Let's look at a sample prompt. Hardening the API against SQL injection. The router scans this string and isolates the specific keywords. It pulls SQL, injection, and hardening, then looks up their individual values in a local JSON file. SQL might have a weight of 5.2, injection 9.1, and hardening 2.5. The system adds these numbers together to generate a cumulative confidence score. Because the total exceeds our threshold, the code immediately branches down the specific security routing path. Every time the specific routing leads to a successful security fix, the system rewards those exact keywords by incrementing their weights by 0.01. The router self-weights its own intelligence based on historical interactions. If a mistake occurs, the system logs it in a trauma memory file. Before the router executes any logic, it checks this file. If it sees a pattern that caused a failure in the past, it short-circuits the logic tree and takes the manually corrected path. Over 18,000 records, the symbolic rules and connectionist weights reach a statistical equilibrium. In our last 10,000 test cases, it routed tasks with 100% accuracy, and it didn't consume a single LLM token. Routing the prompt is only the first step. The system still has to select the right computational tool for the job. When you give a standard agent a static list of tools, it struggles to adapt to edge cases. It has no memory of which tool actually works best for specific categories of problems. This beta distribution curve solves that. System 4 employs a Bayesian governor. Instead of treating all tools equally, it tracks a precise success-to-failure ratio for every tool in the registry. Using a technique called Thompson sampling, the orchestrator probabilistically samples these curves to pick the tool mathematically most likely to succeed based on historical data. If the governor's confidence in all available tools drops below 20%, a circuit breaker engages. The loop halts, and the system asks the user for clarification rather than guessing. Applying this probabilistic sampling to tool selection effectively eliminates the infinite error loops common in standard agent architectures. Even with perfect routing, the agent still needs context, but you cannot feed a 500-file repository into an LLM and expect high-quality logic. Standard retrieval-augmented generation blindly chops text into fixed-size chunks. This creates the blob problem. You get a random paragraph of code without the surrounding imports or class definitions required to actually understand it. This diagram shows System 3's solution: hierarchical parent-child indexing. We strip the implementation code out of the files, leaving behind only the pure structure. The system takes the entire source file and saves its metadata as an overarching parent node in the vector database. Then it isolates the individual function signatures, the precise names and arguments, and saves them as distinct child nodes, visually and semantically wired back to their specific parent. By utilizing a programming language's abstract syntax tree, the memory layer extracts these exact structures reliably, creating a dense, highly efficient repo map. This compression technique allows us to fit the structural outline of a massive codebase into a standard 8,000-token context window. Hierarchical chunking guarantees that the execution layer receives highly precise functional snippets, while simultaneously retaining the overarching structural awareness required to write code that actually compiles. We now have accurate routing, probabilistic tool selection, and highly compressed memory. Here is how they all execute in real time. This split timeline shows the dual pipeline. Initial code generation is handled by System 1, utilizing a lightweight, fast cloud model. This initial draft streams directly to the user interface. This ensures the user experiences zero latency in the response. But while the text is streaming, System 2 wakes up. This is a 26 billion parameter local model acting as a senior supervisor. It runs a background auditing process, reviewing the cloud model's code for logic flaws or security vulnerabilities. If the local supervisor finds a critical flaw, like an SQL injection risk, it rejects the solution and immediately deploys a correction payload to the interface via WebSockets. Asynchronous auditing provides the speed of lightweight cloud models, alongside a localized security review that never leaves your hardware. Every rejection triggers the final step of the feedback loop, where the system updates its internal databases in parallel with the user-facing correction. A single rejection simultaneously shifts the Bayesian beta distribution for the tool that failed, writes the error into the trauma memory, and penalizes the System 4B keyword weights that led to the bad path. To scale autonomous agents to production levels, you cannot rely entirely on an LLM context window to manage probabilistic decision-making. The math simply does not support it. The future of local AI architectures lies in highly optimized, deterministic code layers that intelligently and automatically manage their own memory and logic.